I have to be honest with you.
Oh,
When I saw what we were covering today, I had a distinct moment of panic.
I can imagine.
Usually we dive into history or tech trends or maybe some obscure psychological study.
hmm
But today,
Today we're tackling the big one,
the big one, we are talking about Einstein.
the heavy hitter. And I totally get the panic. I think for most of us, the phrase theory of relativity just triggers this immediate.
Imposter syndrome.
Exactly. It feels like you need to be in a lecture hall at MIT just to have an opinion on it.
Right. It feels like it belongs on a chalkboard covered in Greek letters,
Mm.
not in a casual conversation.
Mm.
I mean, my assumption has always been that unless I'm ready to do calculus, I should probably just stay out of it.
But we have a source today that suggests otherwise.
We do. We're looking at a fascinating transcript today.
A conversation between two friends, Arav and Ria.
And what I love about this is that it's not a lecture. Arav is the skeptic. He's the guy saying, come on, this makes no sense.
And Ria is the explainer, trying to translate the universe into plain English.
And that is exactly what we're going to do in this deep dive. We're going to piggyback on their conversation to unpack the really mind-bending stuff.
Yeah, we need to talk about why time isn't what we think it is.
And why gravity is actually geometry. And this is the part that surprised me. Why none of this is just theory.
Right. It's actually happening in your pocket right now.
It is.
And the mission here isn't to make you a physicist. It's to get to that point where the world looks a little different than it did 20 minutes ago.
So let's start where Arav starts. He walks into this with the same assumption I have, and I think everyone listening has. He assumes that time is this fixed stage. Like a minute is a minute.
Always.
If I set a timer for 1 minute here, and you set a timer for 1 minute on the moon, they ring at the same time. That feels like common sense.
It's the ultimate intuition. Isaac Newton, the grandfather of physics, he believed this too.
Right.
He viewed time as this master clock ticking away in the background of the universe.
The universal clock.
Yeah. It didn't matter what you were doing, sleeping, running, flying. The clock kept ticking at the same steady rate.
Right. If I'm late for a meeting, I can't blame the physics of the universe. I'm just late.
You're just late. But Ria stops Arav right there.
She drops this bomb that time is not fixed. She says it's variable.
And we need to really sit with that for a second. Ria isn't talking about the perception of time.
No.
She isn't saying time flies when you're having fun. She is saying that a physical second, the actual duration, it changes.
Which sounds insane.
It does.
If I have a high-precision atomic watch and I shake it or move it, it should still tell the time, right?
Well, according to Einstein and Ria, no. She highlights two specific levers that warp time.
Okay.
One is speed, how fast you are moving.
And the other.
The other is gravity, how heavy the stuff is around you.
Okay, let's break these down because this is where my brain starts to hurt. Let's start with speed.
Okay.
Arav asks the obvious question. So you're telling me time can slow down?
And Ria introduces this concept of time dilation.
Time dilation. It sounds like Star Trek technobabble.
It does, but the principle is actually surprisingly clean, even if the result is weird. The rule Ria lays out is simple.
Which is?
If you travel really close to the speed of light, time moves slower for you compared to someone standing still.
Okay, but why? I feel like we always hear fast equals slow time, but does the source give us the why?
It sort of implies it. Think of it this way. The universe has a strict speed limit, the speed of light.
Nothing can go faster.
Nothing. So if you are in a spaceship zooming along, you are using up a lot of your motion allowance just to move through space.
Okay.
And because you are diverting so much energy to moving through space, you actually have to move slower through time.
Well, you can't maximize both.
You can't. It's a trade-off.
So it's like, if I max out my speed across the map, I have to sacrifice my speed through the clock.
That is a fantastic way to visualize it. Yes.
Yeah.
If you're standing still, you are moving through time at maximum speed.
And if you're at light speed?
You effectively stop moving through time.
So Arav, being the practical guy he is, asks the question I would ask. He says, so if I went to space super fast and came back, I'd be younger than you.
The twin paradox. It's a classic.
And Ria says, exactly.
Yeah.
But I want to push on this. Does she mean he would just look younger? Or...
No, she means biologically, chronologically younger.
Really?
Yeah. If Arav leaves Earth at near light speed for what feels like 5 years to him, he might come back and find that 50 years have passed on Earth.
So Ria would be...
Ria would be an old woman and he'd still be in his prime.
That is terrifying.
Yeah.
It basically means time travel into the future is possible.
It is. You just have to go fast enough.
Arav has a hard time with this. He says, That sounds like science fiction.
Mm.
And I'm with him. It feels like a writer's room trick, not reality.
It does feel like fiction because we never experience it. We move at, what, 60 miles per hour in a car?
Maybe 500 in a plane.
Right. At those speeds, the time dilation is so tiny, it's unnoticeable. You need to be hitting hundreds of thousands of miles per second to really see the gap.
But Rhea makes a point to tell him this isn't just theory. She says it's been proven with experiments.
And this is where we get to the part that affects your daily life. Because Rhea brings up the GPS.
Right.
And I think this is the most important aha moment in their entire conversation.
Yeah, she mentions that GPS satellites have to account for these effects. Yeah. Let's dig into that. I feel like people say GPS uses relativity without really explaining what that means.
Of course, you just look at the blue dot on your map.
And get annoyed if it's drifting.
Right. So think about what a GPS satellite is doing. It's screaming around the Earth at about 14,000 kilometers per hour.
Okay, so it's fast.
It's very fast.
Yeah.
So based on what we just discussed, special relativity, what should happen to its clock?
Well, if it's moving fast, its clock should be ticking slower than my clock here on the ground.
Correct. It loses about 7 microseconds a day because of its speed. But, and here is the tug of war, Rhea also mentioned that gravity affects time.
Right, the second lever.
General relativity says that gravity slows time down. The closer you are to a massive object like Earth, the slower time moves.
Okay, so I'm standing on the ground, deep in Earth's gravity. The satellite is way up in space.
Exactly. The satellite is 20,000 kilometers up. The gravity is much weaker up there.
So its clock should be ticking faster than mine.
Faster, because it's farther away from the heavy Earth.
Whoa. So you have two different laws of physics fighting each other.
That's it.
Speed is trying to slow the clock down,
Yeah.
and low gravity is trying to speed the clock up.
Exactly. And they don't cancel each other out perfectly. The gravity effect is actually stronger.
How much stronger?
It speeds the clock up by about 45 microseconds a day.
So when you do the math,
Plus 45 for gravity, minus 7 for speed. The satellite's clock runs about 38 microseconds faster than yours every single day.
38 microseconds.
Yeah.
That sounds like nothing. Why does Rhea say the system would fail without this?
Because light travels really, really fast.
Oh,
In 38 microseconds, light and the radio signals from the satellite travel about 11 kilometers.
oh.
Yeah. Oh, is right. If the engineers didn't program Einstein's equations into the satellites to correct for that drift,
My GPS would be off by 11 kilometers a day.
every single day, within a day or two, you'd be looking for a coffee shop in Chicago and your phone would think you're in Lake Michigan.
That is wild. So literally, for me to find the nearest Starbucks, we have to account for the curvature of time and space.
We do. Einstein is quite literally navigating your car.
That definitely grounds it. It stops being magic space math and starts being utility engineering.
Exactly.
But this brings us to the second half of Arav and Rhea's chat. We've talked about speed, but then Arav asks, what about general relativity?
This is the shift from the time aspect to the gravity aspect, and honestly, this is the bigger conceptual leap.
Rhea drops a line here that I think is the hardest hurdle for people. She says, Einstein said gravity isn't just a force.
Which goes against everything we are taught in school, right?
Totally. I mean, Newton again, right? We're taught that gravity is a force. The Earth pulls the apple. The sun pulls the Earth.
It's like there's an invisible rope connecting them.
Yeah, a tug. But Rhea explains that Einstein saw it differently. She says gravity is the bending of space and time caused by massive objects. This is where Arav gets a little lost, and honestly, I do too. Yes, so Earth bends space, and that's why things fall down.
Right.
I'm trying to picture empty space bending. How do you bend nothing?
That is the million-dollar question, and Rhea uses the absolute best analogy for this.
The rubber sheet.
The rubber sheet analogy. It's famous for a reason.
I love this part.